What's up, everyone? Today we're talking about ground effect. So what is ground effect? Ground effect is where you have something that produces a lift, for example, an airplane, and it travels close to the ground. That changes the aerodynamics of the aircraft. And we're going to be discussing how that happens, what it does, and why. And to do that, we're going to look at two different papers. The first one is called Experimental Investigation of a Wing in Ground Effect Craft. And you can link in the description for this one. And let's go through it here. So they say in the abstract, the aerodynamic characteristics of the wing in ground effect craft, so a WIG craft, this is often what's called a craft that has been designed to actually fly near the ground to take advantage of this ground effect. Craft model of a compound wing was experimentally investigated with and without end plates. And the reason why I chose this paper was because it is a pretty cool paper. It has ground effect and end plates. The end plate is, if you look at any aircraft really these days, at the end, near the wingtips, they have these parts that go vertically, so either up or up and down, and they're end plates, and they affect the induced drag. They're there to reduce a lot of the induced drag and make the aircraft more efficient. So they're looking into those and ground effects. So it was a pretty good combination. So I thought that this would be an interesting one to review. So going on, lift and drag forces, pitching moments, and the center of pressure were measured with respect to the ground clearance and the wing angle of attack. So they're looking at how all these forces changed and the stability of the aircraft as you move it closer to the ground. And then they go on and say the ground effect and the existence of the end plates increase the wing lift to drag ratio at low ground clearance. So what it means is it's very successful. Now they say this in the abstract, which I'm not a fan of. I mean, they're giving away everything in the abstract. It's like being on a first date and you just give away everything. There's nothing left for anyone to look forward to for the rest of the paper. So we're going to go through it anyway, though. Now, should we care about ground effect? Do I care about ground effect? Yes, I do. And the reason why is because it can change aerodynamics for the better. So let's talk about it. The ground effect is a phenomenon where the lift-to-drag ratio of a body will increase while it is cruising at a very close distance to the surface of water or ground. So the lift-to-drag ratio is a measure of how efficient a body is producing lift. The higher the value, the better. The development of WIG crafts, so wing in ground effect crafts, originated from observations made of the landing performance of aircraft in the 1920s. So this is not just something that happened in the 1920s, it's when they observed it first. But even to today, anytime you go out to take, let's say, an airplane and you're trying to land it, often inexperienced pilots will have a very difficult time landing aircraft because the closer you get to the ground, the higher the lift increases, and you really struggle to drop enough speed or have a high enough angle of attack to then, in some cases, you have to stall the aircraft to get touchdown. So it can produce problems, and there are ways to get around that. So the lift and drag that are produced by a wing define the performance and general abilities of the craft that it supports. If the wing is designed properly, the lifting surface near ground generates higher lift at smaller ground clearances. However, the drag decreases with decreasing ground clearance. So that's cool. You not only have an increase in lift, which is what you want, you have a decrease in drag, which is also what you want. So we're talking about what it does. Let's go into how they work, the theory behind it. So for this is the second paper. This is the first paper I was just reading from. This other paper that I'm using, it explains it quite well. So let's look at this one. It's called CFD Simulation of a Wing in Ground Effect UAV. The link to this is also in the description. So this is a picture that they have that explains how ground effect works. And they boil it down to two factors. The first one is, so if you have an aircraft and it's flying in the air, you have this system of flow. So flow moving from the pressure side of the wing around and to the top surface, the suction surface. When you move the aircraft to the ground very close, you now squish all that pressure underneath outwards. And this, they say, is it effectively increases the span of the wing. So instead of the span being from wingtip to wingtip, it's now further out because this air that's underneath this high pressure air can't really escape very easily. So it effectively increases the span of the wing. That results in an increased lift coefficient, because you're effectively kind of cheating the system where you have a regular geometry, but you're maximizing the effective lift, the effective wingspan. So that's how you get increased lift. How do you get a reduction in drag? It also comes down to this effect here. Because you're near the ground, the air trying to escape from underneath the pressure side to go to the suction side has a lot more resistance, which means it can't really do that as easily. That then reduces the induced drag, and you get a reduction in drag, which is pretty cool. So coming back to, so that's how the ground effect works. Coming back to this paper, which now goes into some experiments which tested this particular type of aircraft and in different conditions, different heights from the ground, and with a different configuration, the end plates. So end plates help to increase the performance of the wing through moving its center of pressure forward to the leading edge. The influence of the end plates on the aerodynamic characteristics of small aspect ratio wings was studied by Park and Lee and like a billion other people. Like a lot of people have investigated this. And, you know, Boeing, Airbus, they all have winglets or sharklets. They're different names for end plates. According to their study, the reduction of the wingtip vortex will develop a substantial rise in the lift and lift-drag ratio, which can be developed by end plates. It can be seen from the literature review that improving the aerodynamic characteristics of the wing in proximity to the ground by different means, such as the end plates, the configuration of the wing is one of the important parameters in designing a weak craft. The improvement of the wing can increase the range and endurance of flight, which is all true, and decrease the fuel consumption and CO2 emissions. In this research, the aerodynamic characteristics and static stability of the weak craft was experimentally investigated with and without end plates. So we've been talking about lift, drag, and lift drag ratio. Let's talk about the static stability, because they say here the static stability of this aircraft was investigated. So what is static stability? It's very well known in aeronautical engineering, but in aerodynamics, generally speaking, often it's not that known. And effectively, static stability is the ability for any object, including an aircraft, to, when it's perturbed, to return back to the position that it was before it was perturbed. So let's say an airplane flies through a gust. That gust might produce a pitching up moment, so nose up. Now, once the gust is over, if the aircraft is statically stable, it will then tend back to the position it was before the gust hit. If it's not statically stable, that gust will throw the aircraft off its original path, and then it will go into some other orientation and probably stall and create a lot of safety problems. So generally speaking, for every aircraft, you want it to be statically stable. Now, that's true for commercial, like passenger and cargo. There are some considerations. Sometimes you don't want it to be statically stable, but they're few and far between, and usually for military applications. So for example, one common example was a fighter jet from Sukhoi, and this was back in the 80s and 90s. They actually made the aircraft statically unstable. And the reason why they did that is because if you make something statically unstable, it's more maneuverable. It can change direction very quickly without this restorative force moment trying to restore the position that it was in beforehand, the orientation. So by making it statically unstable, you can increase maneuverability. The problem with that is if you make it too statically unstable, it requires not only a lot of input from a pilot, but also usually an input that the pilot cannot actually do. You need to have two quick reflexes to do it, and humans aren't able to do that. So they need to use computers to change the control surfaces to account for any of these instabilities. So overall, you want an aircraft to be statically stable. The trade-off that comes with that is obviously you get safety, but the trade-off with that is it becomes less maneuverable. If you don't mind having a lower safety margin, you can then make the aircraft more maneuverable if you reduce the static stability. That's how static stability factors into aeronautical engineering. So with this paper, they were looking at the end plates and ground control, ground clearance with these parameters. So let's look at the craft that they were looking into. So this is the paper here, and let's go down to figure 2 and figure 3. So these show the wings that they're looking at. So the experiments were carried out on a weak craft model that used a new compound wing configuration as shown in figures 2 and 3. So this is the wing here. The compound wing was composed of 3 parts, a rectangular wing in the middle and 2 reverse taper wings at an anhedral angle at its sides. So effectively you have this middle part here is flat, then on the 2 sides they come down. There's some they call it anhedral, which means it just comes down at an angle. So effectively the wing looks like that, it's curved. Now, the wings were NACA 6409 airfoil sections. So what does a NACA 6409 wing mean? It means that it has a 9% thickness ratio. So the actual thickness of the wing is 9% of the chord so the distance from the leading edge to the trailing edge. And it has a camber of 6%, which means that it has, again, relative to the chord length. So the experiment, and this is the model that they looked at. So with end plates and without end plates. So the setup, the ground clearance, which was H on C, and different angles of attack alpha, the H on C range from 18% to 25%, of 0.18 to 0.25, which work out to be 18% and 25% of the chord. And from alphas 4 degrees and 6 degrees. The ground clearance was defined as the distance ratio between the wing trailing edge center and the ground surface to the root chord length, as I mentioned. So that's the percentage coming in. In this study, the floor of the wind tunnel was used as a fixed flat ground. So let's talk about that a little bit more. Now, it says the floor of the wind tunnel was used as a fixed flat ground. What does that mean? It means that it's a typical wind tunnel that you'll see almost everywhere, where the surface on the ground is just a flat sheet or whatever it is. So what happens there? When the flow goes over any surface, as we know, in real life, a boundary layer forms. Now in CFD, you can always assume like a slip condition and whatever, but in real life, it's always a non-slip condition. So that means that a boundary layer always forms. Now, how does that differ to real life? In real life, when you have an aircraft and you're flying over the ground, the aircraft is moving, the ground is not, and there's no air going over the ground. Let's assume that there's no wind. So if that's the case, if it's a still day, there's no boundary layer forming over the ground. The aircraft is flying over, and the velocity of like very close to the surface is pretty much the same as what this aircraft is seeing when it's close to the ground as well. So in reality, there's no boundary layer forming in this region. So in a wind tunnel, when you have just a fixed flat ground, you do have a boundary layer forming. So that's a difference between what you have in real life when you're flying very close to the ground and in a wind tunnel. Now, how can you get rid of that boundary layer in a wind tunnel? There are ways to do that. One very easy way is you make a splitter plate. So you have your boundary layer, and then you have a splitter plate over, let's say you put it 30 centimeters above the ground surface, and then that's effectively creates a new fresh flow. And then you put your aircraft above that. Alternatively, you can use what's called like a boundary layer suction system, where you suck out that boundary layer, and then you re-inject perhaps some higher momentum flow to account for any irregularities in the flow that you've now created, to then get rid of that boundary layer. That's some pretty complex stuff. So let's go on to this paper here. The lift coefficients of the Werq craft model with and without end plates are shown in figure 6. So let's go to figure 6 here. So this is just the aircraft in the wind tunnel, and it's quite a big wind tunnel. It's 1.5 meters tall and 5.5 meters long. And this is all the results here. As expected, the lift coefficient of the Werq craft model with end plates was higher than the lift coefficient of the Werq craft model without end plates. From the previous figure, it is clear for high angles of attack and lower ground clearance end plates significantly enhance lift coefficient. So not only that, but so what they're saying is that the end plates work very well. But even if you just look at this figure without even worrying about the difference between the end plates and the end plates, no matter which configuration you look at, as you go closer to the ground, this lift coefficient increases. So that's pretty cool, no matter what configuration you have. Now then we have the drag coefficient, and similar here, no matter what configuration you have, the closer to the ground you get, the lower the drag, and that's because of that induced drag. So, and they say here, the increment of drag can be related only to the angle of attack and ground clearance. For higher angles of attack and ground clearance, drag coefficient increases up to 11% and 5% respectively. So when you go higher, the drag coefficient increases. So that's why sometimes they design aircraft to travel very close to the ground to take advantage of this and make your aircraft more efficient. The comparison of lift-to-drag ratio between the wing-craft model with and without end plates is shown in Figure 8. So Figure 8, where is that? It's down here. Here we go. So again, as you go closer to the ground, the lift-to-drag ratio increases, and they said for low ground clearance end plates, the lift-to-drag ratio increase up to 45%, which is huge. Like literally in aircraft, if you can get like a 2% increase, that's like a game changer. So 45% is massive. And then they have the pitching moments. So the pitching moment is how much the aircraft wants to pitch, so nose up or nose down. It's one of the static stability criteria. The pitching moments were measured about the point which was 40% of the chord length from the leading edge. The CMZ being positive for the wing with end plates consistent with the prior discussion about stability for a wing. The second parameter that has a main effect on the stability of wing craft is the center of pressure, which is down here. The distance between the leading edge and center of pressure on the wing is defined as XCP, so here. And then now they've normalized this to the chord to give it a percentage base. Figure 10 shows the center, this one here, shows the center of pressure for the wing craft model with and without end plates. In general, the position of center of pressure of the wing craft model shifted towards the leading edge due to the effect of end plates. This effect is expected as pitching moment reduces due to end plates. And finally, they looked at the height of static stability of the wing craft model for both with and without end plates was negative with respect to ground clearance. So that means that the craft is statically stable for both, which is good for safety reasons. So that's the end of this podcast. Make sure to like and subscribe. We also have the International Aerodynamics Conference in October, and it's for everyone who loves aerodynamics, so you can go there if you love aerodynamics. If you don't love aerodynamics, you can still come along, but you need to pretend like you do, like everyone else. Link in the description. We make lots of instruments here at Premier Aerodynamics. For example, the atmosphere hall. This reduces a lot of the errors in your experiment, so make sure to check it out and pick one up for yourself. You will have better results, and better results mean more papers mean more funding, everyone's happy. And finally, check out the courses that we do here to make you a better aerodynamicist. We do CFD, experiments, and theory. All right, so that's it. Peace out, amigos.